Welcome to another instructional snippet. Today we will be working an example of applying conservation of mass to a control volume. This example is rather simple, but I hope it demonstrates the general method to set up more challenging problems. Let's review some prerequisite knowledge. Average velocity is calculated with the equation below. By definition, a uniform velocity over an area is the average velocity. All velocities in this video are average velocities and just the symbol v will be used. A knowledge of a unit normal vector and the vector dot product will be useful, as is basic integration. Here is the problem statement and the corresponding diagram. The open tank contains water, and is being filled through pipe 1 and pipe 3, water is discharging through pipe 2. If the water level, h, is constant, what is the velocity, v2? Below is the provided information. Now let's start solving the problem. Recall, we are trying to find the velocity at point 2. We can use conservation of mass for a control volume. It is shown below. Let's start simplifying. If the water level in the tank, h, is constant, then it is steady state. We will also use the definition of volumetric flow rate, Q, and how to calculate an area using the diameter. Next we need to define the control volume. The conservation laws apply to any control volume.
I can't change the laws of physics.
However, we must choose a control volume that allows us to solve the problem. We will choose the water in the tank as the control volume. Next we identify the surfaces where the mass flux is not zero to simplify the surface integral. There are 3. The integral conservation of mass equation expands as shown below. Let's review the dot product in the surface integrals by looking closely at surface 1. The unit normal vector is pointed out or away from the control volume. At this surface the velocity is coming into the control volume. The angle between the unit normal vector and the velocity vector is 180 degrees. The dot product returns a negative sign. In conservation of mass for a fixed non-deforming control volume, inflows are negative and outflows are positive.
Logical. Flawlessly logical.
Now let's continue to solve the problem. As stated previously, all of the given velocities are average velocities, so we can simplify the above. Recall that the average velocity times the flow area is just the volumetric flow rate, Q. Putting this together allows us to solve for the velocity at point 2 as shown below. Below is some arithmetic, solving for areas 1 and 2 with the provided data. Now let's substitute in all of the provided and calculated data. We get that the velocity at point 2 is 4.36 meters per second. Are we done?
No.
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 No. No.
No.
No.
No.
No.
No.
No.
That's right, we need to double check our units. Looks good, we're done. I hope you found this instructional snippet useful. If so, please like and subscribe. Thank you and have a great day.